Proof by induction, baby. We've all been here before. So, every time I see this and it doesn't give credit to Gauss, it bothers me. So, if you like history, there's some little history about this. Like the OG Gaussian sum, yeah. I think we all know the story at this point. We've all been through discrete math. But, you know, as it says down here, treat it as a famous anecdote rather than a perfectly documented transcript of a single classroom moment. So, yeah, this is a Gaussian problem. Oddly non-problematic for a white guy in math history. So, got to give the guy some credit every time you get a chance. So the problem statement, we're going to take the Gaussian sum and show that the Gaussian sum squared equals the sum of cubes. That's a lot of words that say the same thing. So proof by induction, we've already been here. We take our little sum there and we do our P of 1 case, which is base case, could be a P of 0 case, which we all learned in discrete math. And what do you know? It works for 1. So let's assume that for all, well, in this case, all natural numbers greater than 1, greater than or equal to 1, that it holds true. And then we're going to show an inductive step. So for all natural numbers plus 1, does it work? We're going to assume yes, and then when we don't find any contradictions, we're going to be like, yeah, what do you know? It works. One of the most famous sums is it's the real deal. So we know this. We have our k plus 1, and yeah. So starting from the definition, we're going to take our k plus 1 and then our s of k and then add k plus 1. And then the real math, which I think at this point we've all done, 50 times by now. So we'll factor out our k plus 1 and then, you know, write our 1 as the 2 over 2 so that we can maintain the 1 over 2 part, or depending on how we write the sum, sometimes it'll just be the entire sum over 2. And then we get the proof by induction that the S of n, the sum of n, equals 1/2 n times the quantity n plus 1, or n times the quantity n plus 1 all over 2, depending on how you want to write it. So for all natural numbers n, the sum of them from 1 to n equals 1/2 n times the quantity n plus 1. So from here, when I first did this, like, you can just square that and then show that it gets to the same same format as the sum of cubes. But I'm not sure if that's what the intent was. So we're also going to do proof by induction for the sum of cubes. So our base case, our P of 1 case, what do you know? 1 cubed equals 1. Also, imagine that. One of the most famous sums, like, checks out. So then we move on to the inductive hypothesis of k greater than or equal to 1 for the natural numbers, and we're like, okay, well, if 1 works, let's just assume they all work, and then if we don't come up to any contradictions, then we win. And this is almost the exact same format as the base Gaussian sum. So almost the exact same thing. We factor out a k plus 1 squared, and then we got to maintain our over 4 so we can keep it in the same format, and put everything over the common denominator, And we already, like, at this step, we actually already have pretty much the same format as what the question was asking. So I think if we were purely looking at the original question, be like, look, they match. But, you know, we're going to go through the entire thing. And so we've proved that the sum of cubes equals 1/4 n squared times quantity n plus 1 squared. For all natural numbers, n greater than or equal to 1. So for part A, we square that. And this is what I was saying, is like, we could just do part A and square it and then show that it matches. But yeah, I guess we should prove both and then prove that they match, because that's kind of what the question says. So then we have down there the sum of cubes. So 1 cubed plus 2 cubed plus ... n cubed equals the quantity 1 plus 2 plus ... n squared. And this should look familiar to everybody. I think there's some people that didn't take calculus 2 because it's on a different track than some people are on for prior to the BSCS. But all of these should look familiar because they're the the definite integrals formats, the Riemann sums for the, you know, x dx or x squared dx or x cubed dx. There's the whole set of Riemann sums to expand. And then the higher degree polynomial integrals produce higher power sums. That is one reason that these summation formulas matter. They're not just number patterns, but part of the machinery used to pass from finite sums to exact area under the curve. So, yeah, they should look familiar. We should have all seen these a lot because it's all connected, man.